Okay. The third term is the viscous stress tensor. Is the effect of the viscous stress tensor. And it's so writing in such a way, it's quite non-intuitive to figure out. And for me, the most easy way to figure out the effect is think about the incompressible form. Actually, let me write out the incompressible form. So if you have an incompressible flow with uniform density, okay? So if you have uniform density, this baroclinic torque is gone, right? You don't have baroclinic torque. And the rho is a constant, so let's multiply the whole equation by rho. So what we get is d omega, so I'm going to say incompressible. So multiply the whole equation by rho, I get this equal to omega dot grad u. This is gone, and I'm gonna get this 1 over rho is also gone. Oh, but there is another 1 over rho. I'll just pull it outside. So that's the curl of the divergence of the viscous stress, and the viscous stress for Newtonian fluid is nu times grad u plus grad u transpose. Okay, and here I want to point out why for incompressible flows you don't need to include that term. Okay. Because if you write in Einstein rotation, that is partial ui, partial xj, right? That's the let's see, this is equal to that. And the transpose is just switching the indices. All right. Okay, so now let's look at for constant viscosity. For constant viscosity, what does the divergence do to this term? So the divergence is basically the divergence, and in particular the divergence taken. So the divergence taken on these two terms. You can see one of the term is basically taking a second order derivative. So one of these two terms, grad u plus grad u transpose, is equal to partial square ui partial xj square. So that's one thing, plus partial square ui partial xi partial xj. And this particular term is the derivative, is the j directional derivative of what? The divergence of u. So if the divergence of u is equal to 0, then this term is gone. And you only need to consider the Laplacian of the velocity for your viscous stress tensor. Right? So if you replace this term with the simpler form of the Laplacian, what you get is still this, plus mu over rho, which is the kinematic viscosity. Let's write it like that. And we have the curl of the Laplacian of velocity. And these two can commute, right? Because they are both Eulerian derivatives. So this is basically the Laplacian of omega itself. Okay. So now these two terms left over are the two terms that applies for incompressible and compressible flows, and their effect is quite similar. So this term is like a diffusion of the vorticity. That's why for the Rankine vortex we have shown as an example. We have an infinite gradient on the omega field near the border of that vortex core. And following this term. If we have an infinite gradient, we have, actually you only need to have an infinite second order derivative for you to have an infinite time derivative of the vorticity. So basically your vorticity is going to diffuse out of the vortex core. All right. And the first term for the ranking vortex is actually 0. Because what is the vector direction of omega in the ranking vortex? It points out, inside the board, right? So for the particular example, it points inside the board. And any gradient of velocity is 0 in the same direction, right? Because it's a two-dimensional flow field. Actually, the same thing holds for any two-dimensional flow field. For any two-dimensional flow field, the vorticity always points in or out of the third dimension, and the velocity gradient is always 0 along the same direction. So for 2D flow field, this particular term contributes nothing. It's only useful for three-dimensional flow fields. And that's actually, I would say, the reason why you have no turbulence in 2D. Okay, so this, in turbulence happens in 3D. This term is the term that transfers the larger scales in your flow field into smaller scales. So you're going to see that the effect of this term. So right now, so let's analyze the effect of this term. So assuming you have 0 viscosity, or viscosity is not important locally in the flow field, then you have a equation, vorticity transport equation like that. Does anybody still remember what we did in the last lecture? We are looking at the evolution of a material line. I guess that means no. We analyze the evolution of a material line. So we look at a line that sits in the flow field and how it evolves at infinitesimal time later. And the equation we derived is this. Right? Anybody still now remember? Look at these two equations. They are the same. Right? So for in viscous flow field, what we say about this is that a vortex line moves with the flow. So if somehow you can have a magical die that marks a particular vortex line, by that I mean a line that is always tangential to the local vorticity field. Right? So if you draw a line basically tracing along the vorticity omega direction and you use colors to mark that line. Then after some time, that die has been transported in another location. What do you think about the direction of that die line after some time? What does this say? Oh, this tells me that the vorticity is still going to be aligned with that particular line, right? Okay. So the movement of the material line, where you mark with some color or color dye in the flow field, is the same as the evolution of the vorticity vector. So after some time, that line is still going to be aligned with the omega direction. So basically, by following a line in the flow field, you know two things. One is, what is the direction of the vorticity now? Because the direction is going to be aligned with that line. Two, you also are going to know how the strength of the vorticity is going to evolve. Okay, how is it going to evolve? It's stronger if the line is stretched. It's weaker if the line is squashed. Right? So that's why you have no vorticity stretching or tilting or whatever in the two-dimensional flow field, because the vorticity points in the third direction, and that line is always moving as the same line, right? So, but in a 3D flow field, that's not the case. And let's take an example. Let's look at an airplane, okay? And an example where you have a lot of vortex stretching is around the wing fuselage junction. So before the wing fuselage junction, is there any vorticity in the flow field? From the wingtips, but like we are looking at a straight wing here, so there is no, the flow doesn't go from the wingtip to the root or the other way, right? But there is fuselage upstream of the wing. So is the fuselage going to create any vorticity? Yes, in the boundary layer, right? And let's consider upstream of the leading edge. What is the sense of vorticity? Which direction does omega point to? In the boundary layer. Up? Up? You sure? We are looking at the near side of the fuselage. Oh yeah, it's up. Yeah, sorry. I think I was thinking in my computer. Right. So it's yeah. So it's pointing up because it's near the fuselage. It's lower. So it points up, and now the vortex there is going to be evolving because it hits the wing, right? So as a result, there is going to be pretty strong vortices both above and below the wing, near the wing fuselage junction. So now, can somebody tell me what is the direction of vorticity above and below the wing? Which side does, I mean, there is often some small scale separation, sometimes pretty large separation going on over here. So which direction does the flow rotate in that wing fuselage junction? And how did you figure that out?
It's the same analogy that we did with the airline. As it goes over the second, it stretches further along.
That's right. So that's what we actually did in the first lecture. We looked at the material line, how that goes around airfoil, right? So this time, it's not just a material line, it's a vortex line. We know a material line is a vortex line. And we know, in the first lecture, we know that material line gets stretched, right? Because this whole thing has to go around the airfoil later on, even it started as a purely small, very small vertical line. So the vortex gets adapted, it has to stretch around. So initially the vortex line points like that, right? And later on it has to go around the airfoil like that. And later on it has to go around like that, right? So it gets stretched a lot. So that means the vorticity here is strong, and the flow would locally rotate around that direction. And it'll rotate the opposite way beneath, right? I think I'm not drawing a very good thing because this can be interpreted either way, right? So let me draw, this is backwards and this is close to us. This is further from us, right. And above it, it's further from us, close to us, further from us, close to us, right?